Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the Pericyclic Reactions course. So today we'll be discussing about the 1,3 Sigmatropic rearrangement reactions. So as we always do, so we'll try to quickly recollect what we have discussed in the previous class. So we try to understand the definition of the Sigmatropic rearrangement reactions, and then we try to understand the classification of the Sigmatropic rearrangement reaction depending upon the place where the migration origin is there and the place where the migration terminus is there. So depending upon that, so the sigmatropic rearrangements has been, they were classified into 1,3, 1,2, 1,4, 1,5, 3,3, etc. types of sigmatropic rearrangement reactions, right? So and also with the help of Woodward and Hoffman rules, so we try to analyze the sigmatropic rearrangement reactions. So sigmatropic rearrangement reactions may involve the migration of the hydrogen from one end to the other end, or it may also involve the migration of a group from one end to the other end in an unsaturated system. It will cross the at least one unsaturation or the one double bond during the migration process. That is what the sigmatropic rearrangement reactions are. But if it is a hydrogen, you need not to worry about the stereochemistry aspects of the migration. But if it is a carbon atom or a group, so then definitely we need to also consider the stereochemical aspects while migrating, how the group is migrating. Is it retaining the stereochemistry while migrating from one place to the other place, or it is inverting the stereochemistry while moving from the one place to the other place. And also we have seen that the pi system will be in a single plane. So then the migration, depending upon the phase where the groups or atoms are migrating along with the sigma bond, so will give you suprafacial mode of interaction or anterofacial mode of interaction. So as already concluded in the previous class, so as I told you, so we'll see these kind of things with the help of molecular models. So I am ready with the molecular models. So if you see, this is an unsaturated system where these two carbon atoms are with the double bond, and this carbon atom is the saturated carbon atom. So as per the sigmatropic rearrangements, the numbering should start from the saturated carbon atom. So what is the saturated carbon atom? This is the saturated carbon atom or sp3 carbon atom, or as this is at the alpha position to this unsaturation, this is also an alpha carbon atom or allylic carbon atom. So from here, a group or an atom along with the sigma bond has to migrate. So numbering should start from here. So this is 1, 2 and this is 3 carbon atoms. So this sigma bond, this hydrogen bearing sigma bond, if you assume that this is breaking, so if it breaks here, simultaneously the pi bond from here is moving to this place, and then that hydrogen along with the sigma bond might come here. So we call this type of migrations as 1,3 sigmatropic rearrangements of hydrogen because it is hydrogen. If any other group is there, 1,3 sigmatropic rearrangement of a particular group or carbon atom is what we need to say. So this is how the systems which involve in the sigmatropic rearrangement look like, right? So that is the thing. Now, so coming to the analysis of the sigmatropic rearrangement as per the Woodward and Hoffman, we came to know that so orbital correlation method is not successful in explaining or in analyzing the sigmatropic rearrangement reactions. So now we are left over with two options. One is the frontier molecular orbital approach and the other is the transition state aromaticity method, right? So we have also discussed about the frontier molecular orbital theory. So according to the frontier molecular orbital theory, we will now briefly see in what conditions the 1,3 sigmatropic rearrangements are allowed and forbidden, right? So let us quickly go there and see the conditions. We can classify all the sigmatropic rearrangements into two types. One is 4n electron systems, so where 1,3 sigmatropic rearrangements will be falling, and other is 4n plus 2 electron sigmatropic rearrangement reactions, where 1,5 and other sigmatropic rearrangements will be falling. So please note that when we talk about the 1,3 or 1,7 or 1,5, whatever may be the sigmatropic rearrangement reaction, there is an equal participation of the pi electrons besides the participation of the sigma electrons, so sigma bond. So therefore, it is mandatory to represent those systems as either 4n electron systems or 4n plus 2 electron systems instead of 4n plus pi electron system or 4n plus 2 pi electron systems. Okay. So pi should not be given here because there is an involvement of both pi electrons as well as the sigma electrons, that is the pi bond as well as the sigma bond. So therefore, 1,3 and 1,7 sigmatropic rearrangement reactions will fall under the 4n category. 1,5, 3,3 and 2,3 sigmatropic rearrangements will fall under the category 4n plus 2 electron systems. So let us see for the 4n electron systems, so which is 1,3 which is nothing but 1,3 sigmatropic rearrangements. Now, so this 4n electron system is there. How do we do that? So first, see the mode of reaction. And then if there is any stereochemistry involved in the migration center. So is it allowed under specific conditions or forbidden? So we will quickly see these things. So if we are talking about the suprafacial mode of hydrogen transfer or hydrogen migration. So suprafacial mode of hydrogen shift or transfer or migration. So as it is hydrogen, you need not to worry about the stereochemistry because the migrating center is not going to attract any stereochemistry involved in it, right? So therefore, it is not applicable or no need to worry about the stereochemistry of the migrating center. Under thermal conditions, we have also discussed in the previous class, like the hydrogen shift is suprafacially not allowed under thermal conditions. Where it is allowed, then under photochemical conditions only it is allowed. So therefore, what we can write here is it is allowed under photochemical conditions, whereas symmetrically it is forbidden. So how it is forbidden? It is symmetrically forbidden. As per the symmetrical aspects, 1,3 hydrogen shift under thermal conditions is forbidden. So another mode is antero mode of hydrogen shift or transfer. So again, you need not to worry about the stereochemistry involved at the migration center, and now antero mode of hydrogen shift is allowed under thermal conditions, symmetrically allowed under the thermal conditions, but symmetrically forbidden under photochemical conditions. So this is what we have seen in the previous class. Now try to recollect the homomolecular orbital for this 1,3 hydrogen shifts under thermal conditions as well as under photochemical conditions. So if you see, this is a 3 carbon system. So what is the homomolecular orbital for 1,3 hydrogen shift kind of reactions with a 3-centered system, right? So under thermal conditions. So we have 3 molecular orbitals, pi molecular orbitals, psi1, psi2, psi3. And the electronic configuration for that, because we are considering, assuming that the sigma bond is undergoing homolysis, so 3 electrons are there totally. So psi1 will be having 2 electrons, psi2 will be having 1 electron. So all thermal reactions are ground state reactions. Therefore, you have to choose the HOMO at the ground state only. So psi2 is obviously the homomolecular orbital for this condition. So psi2, even number of molecular orbital. So at the terminal, you can see the lobes are opposite in nature. So you are starting with a positive lobe here, and in this corner it is a negative lobe. So let us assume that the violet colors are positive lobes and the pink colors are negative lobes, negative wave functions, right? So now you can see that this is the psi2 molecular orbital, which is a HOMO, and based on this you are going to analyze the possibility of the 1,3 hydrogen shift. Okay. So suprafacial means either the hydrogen should be attached to it. So if this is the hydrogen, 1s orbital of the hydrogen, so it is previously attached at this carbon atom. Now suprafacial 1,3 hydrogen shift under thermal conditions. That means this orbital has to come over here. It has to simultaneously overlap with this molecular orbital wave function and this molecular orbital wave function. So which is quite impossible because the wave functions are different. So therefore, suprafacial 1,3 hydrogen shift is thermally not allowed. Symmetry is not allowing it. So that is what we have discussed here. And next case is anterafacial hydrogen shift, which should be allowed at the thermal conditions, right? So the previous bond is there, the hydrogen orbital is 1s orbital is overlapped with this molecular orbital, positive lobe. So therefore a bond is there. So it has to undergo homolysis, and then simultaneously in a transition state mode, this 1s orbital has to be overlapped with this one as well as anterafacial means the top one. So which is also quite impossible with respect to geometrical aspects, because the 1s orbital is very small and it cannot at a time overlap with these two orbitals. So though theoretically you are feeling or seeing like anterafacial hydrogen shift, 1,3 hydrogen shift is thermally allowed, but as per the geometrical parameters, it is forbidden. So what you need to write here or see here is, though it is appearing as symmetrically allowed, so this is geometrically forbidden. Geometrically forbidden. So this can be proved with a supporting experiment also, literature support. Okay. Now coming to the photochemical conditions. So what is happening here under photochemical conditions? So psi3 becomes the HOMO because the HOMO should be selected from the first excited state. Under first excited state conditions, one electron from the psi2 will move to the psi3. So therefore psi3 becomes the homomolecular orbital for photochemical conditions. So you can see here. So psi3 means 3 minus 1, 2 nodes should be there. One node is there in between these two molecular orbitals, right? This is negative wave function, this is positive. So therefore at the center you can see a node here. And again one more node is there at this point. 2 nodes are there. And as this is a odd number holding my molecular orbital, the terminal carbons will have the molecular orbitals with the same wave function, right? So here it is positive, here it is positive, here it is negative, at the terminal also, terminal carbon atom also it is negative. Therefore, the suprafacial mode of hydrogen shift under photochemical conditions is symmetrically allowed as well as geometrically allowed. So you can see now. So from here it can easily break down and then overlap with this and then form a bond here, new bond here. So from one position to the third position it can easily migrate. So 1,3 hydrogen shifts or suprafacial hydrogen shifts under photochemical conditions is symmetrically allowed. Okay. So anterafacial mode is not allowed. That obviously we can clearly see from this picture itself. So here it is with the positive wave function, and if it is changing the phase and then has to come here to form the bond, this is negative wave function which is symmetrically not allowed. So that is what this table will show you. Yeah, now we have conveniently covered the migration of 1,3 hydrogen shifts, because there is not much to discuss as hydrogen will not offer any stereochemistry. So while migrating or before migrating or after migration. So now we need to think about the migration of a carbon center from the first carbon atom to the third carbon atom in the 1,3 sigmatropic shift. So let us try to analyze the 1,3 group shift using the Woodward-Hoffmann selection rules. So what the Woodward-Hoffmann selection rules will say regarding the 1,3 group shift is that, so when you are thinking about the hydrogen shift, you will need to only think about the antera or supra with respect to the pi system. So when the pi system is there in a plane, the hydrogen might move from the lower phase to the lower phase or lower phase to the upper phase. So if it is lower phase to the lower phase or upper phase to the upper phase, you call it as suprafacial with respect to the pi system. So you are not considering anything with respect to the hydrogen. Okay. So if it is moving from the lower phase to the upper phase, then also with respect to the pi system, you are examining it as an anterafacial mode of 1,3 hydrogen shift. But when we are talking about the carbon shift or carbon atom shift or group shift from 1,3 positions, 1,3 group shift, so you need to consider both the pi center as well as the carbon center. So with respect to pi center, you have to define whether the reaction is suprafacial, and also with respect to the carbon center, you have to define the reaction or 1,3 group shift is suprafacial or anterafacial, right. So based on this criteria, so you will be able to see four different types of possibilities during a group shift. So 1,3 group shift, right. So what are those possibilities? Means all suprafacial migration, all suprafacial migration. That means with respect to the pi center, the reaction is suprafacial, as well as with respect to the carbon center also, the reaction is suprafacial. So the other extreme is all anterafacial. So that means with respect to the pi center, the reaction is anterafacial, and also with respect to the carbon center, it is anterafacial in reaction. So the remaining two things are the pi center being suprafacial, whereas the carbon center, that is the sigma, is acting as the anterafacial partner. So the other combination is pi being an anterafacial partner, while the sigma partner being a suprafacial partner. So these four combinations will give you different possibilities to check whether the suprafacial mode with respect to the pi center as well as the carbon center is allowed under thermal conditions or not, or it is allowed in the photochemical conditions or not. And at the same time, so suprafacial, one partner being suprafacial and the other partner being anterafacial, also we need to analyze whether they are allowed under thermal conditions or under photochemical conditions. So to this extent it is okay. But what is happening when you are considering the group shift? So the group will certainly have different type of substituents as well. The carbon atom which is connected to the allylic carbon atom of the pi system will certainly have different other groups or atoms connected to it. So if all the three different atoms are connected to it, so obviously it becomes the chiral carbon atom, right. So you need to also consider now the stereochemistry of that particular carbon center which is migrating from one end to the other end of the pi system. right? So during the course of reaction, so whether it is intended to retain the stereochemistry as before the reaction or it is changing the stereochemistry after the reaction has to be clearly seen. Okay. So now, so look at this system, right? So this is the pi bond and this is the allylic carbon atom. So this allylic carbon atom is connected to another carbon center, right? So this carbon center is having three different groups. So one being the hydrogen, which is the least preferred one, and the other you assume this blue color one as another carbon atom, which is different other atoms, and this as a deuterium atom. So the red color one as deuterium atom, right? So now you can see around this carbon atom there are different groups. So therefore it is a chiral carbon atom, right? So it is a carbon other carbon atom, this is deuterium and this is hydrogen. So based on the preference, you know how to assign the R configuration or S configuration, right? So now this carbon atom which is connected to the allylic carbon atom via a sigma bond. So as per Woodward and Hoffman, when you assume like this is undergoing homolysis, so this has to move from this end to this end of the pi system. Obviously, while doing so, in a cyclic transition state, when the sigma bond is breaking simultaneously and the pi bond from here is moving here simultaneously. So in a cyclic transition state, the electrons completely involved in it is 4 number of electrons. So therefore, 1,3 hydrogen shift or 1,3 group shift will fall under the category 4n electron systems. Okay. So 4 number of electrons are involved in the group transfer or sigmatropic shift. Okay. So this group has to detach from this carbon atom and then has to come here to the other end of the pi system and connect here. So if it is moving from the lower phase of the pi system to the lower phase of the pi system, so you call this reaction as suprafacial with respect to the pi center only, right? So you need to also look at the carbon atom or the carbon center which is migrating. So you have to see whether this carbon center is also moving on the same phase of it or it is inverting or reversing its phase during the course of the reaction. So suprafacial with respect to the pi system and suprafacial with respect to the carbon center, or suprafacial with respect to the pi center and anterofacial with respect to the carbon center, or the reverse one, or both being the anterofacial. So if both being the anterofacial, that is the least preferred, geometrically least preferred mode of reaction. Okay. So now while looking at the Woodward-Hoffman rules, the first thing you need to see about this 1,3 sigmatropic rearrangements is the mode of reaction with respect to both pi center as well as the carbon center. So mode of reaction with respect to both pi center as well as the sigma center, carbon center. So let us say that it is pi supra plus sigma supra mode of reaction. So that means the pi system is suprafacial and also the carbon system, carbon center or the sigma center is also suprafacial in reaction. So one more thing we need to see is whether the carbon center is going to perform the reaction with retention of configuration or with inversion of configuration, right? So once you see the homolysis, what is going to happen to the carbon center? You see here. So these are the groups attached to it before, and now because the sigma bond has undergone homolysis, this is the molecular orbital of the particular carbon center which is migrating, right? So if this is moving from one end to the other end in the same manner, you call this partner also as, this carbon center also as a supra partner during the course of the reaction. If it has to change the phase and then it has to form the sigma bond using this slope, which you can clearly observe now, it has moved it has turned upside down, right? So what does it mean? It is becoming an antara partner during the course of the reaction. Okay. So when it is suprafacial partner to the suprafacial partner, it will retain the stereochemistry, right? So if it has to rotate in order to migrate and establish a new sigma bond at the other termini of the pi center, so what is happening? The groups have been exchanged and it has to change its stereochemistry. That means inversion is going to happen. When the sigma partner is acting as an antara partner, so obviously after the completion of the reaction, you might see the inversion in the configuration around the carbon center. So that thing we have to clearly note here in this point. Okay. So with the retention of configuration, what the stereochemistry on the carbon center you are observing is retention of configuration. Now let us see when the pi partner is a sopra partner and sigma partner is also a sopra partner, and the condition is like the carbon center has to retain its configuration. You have to see now where it is allowed, whether in the thermal conditions or under the photochemical conditions, and also you need to see where it is forbidden, whether it is forbidden under the thermal condition or in the photochemical condition need to be seen clearly, right. So this is a 4n electron system and you are talking about the allylic system, right. So you have seen already the pi molecular orbitals psi1, psi2 and psi3. 3 pi molecular orbitals will be there for this system and the electronic configuration is this, and homomolecular orbital under thermal conditions is psi2. So homo under thermal conditions, right. So how does it look like? The homomolecular orbital under thermal conditions will look like this one, plus minus. This has one node because this is psi2 molecular orbital. If the group is attached here, right. So now you need to see whether the migration of the group from 1 to 3 is happening with retention of configuration or inversion of configuration. So now we are currently looking for the retention of configuration. So it has to retain the configuration and at the same time you need to check the possibility of the reaction, right. So this is now the psi2 molecular orbital for the allylic system, which is the homo molecular orbital under thermal conditions, right. You see, this is the positive lobe and here is the positive lobe. Psi2 molecular orbital, it will have C2 axis of symmetry. So if it has C2 axis of symmetry means the terminal carbon atoms will have the lobes in the opposite faces. Okay. So now this is the group which has an initial bonding with the carbon 1 here like this. So what you are checking here, you are assuming like this is undergoing homolysis and via a cyclic transition state, it has to migrate to the third carbon atom and need to form a sigma bond. Will it happen really? You see here, the wave functions are different, which is leading for the anti-bonding interaction between these two. So anti-bonding interaction, if you are able to see when you are analyzing the 1,3 group shift with retention of configuration, so it is not possible under thermal conditions. That means what? It is forbidden under thermal conditions. Am I correct? So positive lobes previously involved in the sigma bond, this is undergoing homolysis and via a cyclic transition state in a concerted manner, it has to move to the carbon 3 where you are observing the wave functions in a different manner, which is leading to the anti-bonding interactions. So if it is anti-bonding interaction, so the reaction, the particular reaction with retention of configuration under thermal conditions is forbidden. So it is forbidden where? Under thermal conditions. You see now the photochemical conditions. what is going to happen in the photochemical condition? So, in the photochemical condition, light irradiation, so excitation takes place and therefore, Psi3 becomes the homomolecular orbital. Psi3 becomes what? Homomolecular orbital under photochemical conditions. How does the Psi3 look like? See, so this is the Psi3 molecular orbital. So, you will be able to see two number of nodes, one in between these two here and other one in between these two. Two nodes will be seen. So, positive wave function and a negative wave function, in between a node is there, negative and positive, again a node is there. Okay. So, but at the end of the things, this being a Psi3 molecular orbital, it will have sigma plane of symmetry, mirror plane of symmetry. So, therefore, the wave functions on the terminal carbon atoms will be same, right. So, now you see the possibility of the group transfer with retention of configuration, right. So, previously it has a sigma bond at the carbon 1 and now when we assume like this is undergoing homolysis via a cyclic transition state in a concerted manner, it is migrating to the third carbon atom where you can also see the same wave functions which is going to result in the bonding interaction, right. So, therefore, the carbon center without changing any phase, the pi center is suprafacial as well as the carbon center is also suprafacial. It is migrating from C1 to C3 and it is resulting in the bonding interaction, right. So, therefore, this reaction is possible under photochemical conditions. So, the migration of a group carbon center with retention of configuration when the pi center is a suprafacial partner as well as the sigma center is also a suprafacial partner, that particular reaction is allowed under photochemical conditions. So, what is the next one? So, the next possibility you can check around here is pi partner being an anterafacial partner while the sigma partner, that is the carbon center, still a suprafacial partner, and you need to see the configuration to be retained around the carbon center. So, with retention of configuration only, now you are checking this reaction possibility where the pi center is an anterafacial partner while the supra partner is the carbon center. So, now, so again under thermal conditions for the pi center, Psi2 is the homomolecular orbital where the wave functions are completely different on the terminal carbon atom lobes. So, this is the one, right, Psi2 molecular orbital. Now, you see with retention of configuration, this is a supra partner and this is an antera partner. Pi center is an antera partner now and the carbon center is still a supra partner. If this is the carbon 1 where it is having a sigma bond and now it has to move to the anterafacial mode or that is the opposite phase of the pi center with retention of configuration. So, of course, it is possible, right. So, from here it is migrating and it is moving here. Am I correct? Right. So, bonding interactions are there and with retention of configuration it is allowed under thermal conditions, symmetrically allowed. Therefore, obviously, it will be forbidden under photochemical conditions. You see again the pi partner being suprafacial while the sigma partner being anterafacial. So, you will get almost the same result. So, the third category is possibility is pi partner being suprafacial and the sigma partner being anterafacial. So, if it has to be allowed under thermal condition, how the stereochemistry is changing, we will check now. Yeah. So, this is the pi partner which is suprafacial, that means it is not going to change any phase. So, this is the carbon center with anterafacial mode of interaction. So, now this is the bond here. So, for anterafacial mode of interaction, here the positive lobes are connected to each other resulting in the bonding interaction. So at the other end of the pi center, you can see the negative wave function. Therefore, in order to get the bonding interaction there under thermal condition, this carbon center has to rotate and form a cyclic transition state where these are partially connected to each other. So the bond, sigma bond here is slowly breaking down, while the sigma bond at the other termini of the pi center is slowly making up. Therefore, with rotation, it is able to form the sigma bond here at the other termini. What has happened here? Previously, the carbon center is like this, and now it has rotated like this. That means what? The pi center is still a suprafacial partner, whereas the carbon center has become an anterofacial partner. But as a result of which, the configuration around the carbon center has inverted. The configuration has inverted. So with inversion of configuration, where the configuration is inverting at the carbon center. Why it is inverting? Because the sigma partner, that is the carbon partner, carbon center, is an anterofacial partner, right? So it is still allowed under thermal conditions and forbidden under photochemical conditions. So with inversion of configuration, when the sigma partner or the carbon center is an anterofacial partner, so you can see the reaction possible under thermal conditions but forbidden under photochemical conditions. So what is the fourth possibility means? So both being antera, or you can see like the pi being antera partner and sigma being supra partner with inversion of configuration. So pi center is an antera partner and sigma center is a suprafacial partner, but still you have to get the reaction done where you can see the inversion of configuration around the things. So this type of reaction is possible under photochemical conditions and forbidden under thermal conditions. So with this table you can clearly understand like, so which mode of interaction with the retention of configuration at the carbon center or inversion of configuration at the carbon center is allowed either under photochemical conditions or under thermal conditions. Okay. Example here. So if this is the deuterium and this is the carbon atom or group which is attached and this is the hydrogen. So the sigma bond which is undergoing homolysis is this one. So numbering is like 1, 1, 2, 3. So after 1, 3 sigmatropic shift under thermal conditions, which is possible only with inversion of configuration, you will be seeing this. Okay. So now if you give the preference, this entire portion is first preferred and then this carbon is second and then this deuterium is third. How it is moving? So 1, 2 and 3 in a clockwise direction. So after migration, what has happened means, so this entire portion is first preference, this is 2 and this is 3. With retention of configuration, is it allowed? Suprafacial retention of configuration is symmetrically forbidden. So what should happen now? Inversion of configuration should have happened. So that means after migration, the deuterium would have come here and then the carbon would have come here. So now the preference is like this, 2 and 3. So what is there? So anti-clockwise direction. So it is allowed only under thermal conditions with inversion of configuration in a suprafacial mode. So hope you have understood with the help of these molecular orbitals. Now quickly we will see few examples for the 1, 3 hydrogen shift or group shift in a superficial manner or in an interfacial manner under either photochemical conditions or thermal conditions, whatever is possible. So, if you study this example, this is cyclopropane. If it is connected to an unsaturation this way, this is vinyl cyclopropane. So, vinyl cyclopropane can undergo 1,3 sigmatropic shift. It can undergo 1,3 sigmatropic shift. But what's the problem is, it has to put on with a transition state, cyclic transition state. The reaction has to proceed via a cyclic transition state. So, the cyclic transition state here involves a 4-membered system, 4-membered ring system, the cyclic transition state. So, for that, the reaction has to be taken up to 300 degrees centigrade. If you have to convert this cyclopropane as a vinyl cyclopropane into the 5-membered ring system, you have to heat the molecule for 300 degrees centigrade. So, then only it passes through a 4-membered cyclic transition state and then gives you the final product. So, what is the sigma bond which is breaking up here is what we need to know first. So, this is 1, 2 and 3, and this is again 1. You can take either this carbon atom or this one also. So, this sigma bond or this sigma bond is same only, no problem, right. So, we have considered that this sigma bond is undergoing the homolysis and then migrating here. So, this goes here, right. So, how it is going to happen means via a cyclic 4-member transition state. So, this is the cyclic 4-membered transition state, where you can see one of the sigma bond is slowly converted into a different place, and this reaction can happen at 300 degree centigrade. So, what ultimately we will be getting is a 5-membered system, cyclopentene. So, we have also observed in the previous discussion that 1,3 hydrogen shift is under thermal conditions is forbidden in the superficial mode. Though it is allowed allowed in the interfacial mode, geometrically it is not possible. That is what we have understood. Look into this example. So, if you look into this particular example, there are two possibilities where you can see the 1,3 sigmatropic hydrogen shift. So, you can consider this as 1, 1, 2, 3. So, this is also possible, where this sigma bond can migrate to the third position, right, or else if you see this one, the endo 1, 1, 2, 3. So, this sigma bond can also undergo migration, right. So, if you look into the product, so this is the major product constituting about 83%. So, the other option, this is the minor product. Okay. So if you see the exocyclic systems, unsaturated systems, so the 1,3 hydrogen shift will give you this product, hydrogen shift. So you can refer to many other books and browse, and you can see number of 1,3 sigmatropic shift examples. Please work it out. Okay. So in the next class, we'll try to see the 1,5 sigmatropic rearrangement reactions. Thank you.